Yeah.
You know when the next one is out?
Soon. So.
And what will you do?
So we are planning 2 questions. One is like theory question, one is application. And application will be 2 weeks due, and theory will be 1 week.
Yeah. So I think we'll, yeah, so the application question, I thought like it's good to have both, right? So we'll have one of related to the bias variance trade-off in the modern over parameterized setting. So we'll be setting a question like that. That's more, you deploy, you run these deep networks, look at the results. So something kind of, but there's already a lot of available knowledge, right? There are notebooks, there are pre-trained models, so there's so much available. So we'll give you pointers to where to get started, and then kind of tweak those and see what the resulting outcomes are, what's the bias variance trade-off curve you can observe, and so on. So it will require some amount of compute resources. I know many of the projects here already do some form of deep learning or machine learning, right? So it'll, if you already have access, that's good, but I think I've told before as well that if that's an issue, we can try to solve that problem. So contact the TAs, contact me if compute is the barrier. So I don't want that to be the barrier. And so we'll have these 2 different styles of questions, and I thought the empirical work may require a bit more time, so we'll give you that time.
How many more conferences would there be? Would there be another one next week?
So we'll decide. I think we won't, it won't be like one for every week from now on, because I think, the topics are also getting, in a way, harder to just give simple questions, right? Because they are more complex issues, and they're very much like open problems and new things. So that's why I thought I'd give like this one big empirical research problem. Big again in the sense of for the class assignment, but not give way too many problems, right? It's better to give like few substantial ones rather than a lot. So there won't be a lot of them. I guess we have how many more weeks of lectures? So this is lecture 12. In theory, 8 lectures, I guess, right? Still left. There's 20 lectures, 10 weeks. So, if we kept up, that would be 4 assignments. It'll be probably less than that, maybe 2 or 3. Yeah. And also, I think I wanted a poll, maybe we can do this on Piazza. So one option was to make up the lectures on Wednesday, right? So the Wednesday next week and the week after. The other option is to do it during the study week. So again, I don't know how many of you will be very much busy during the study week versus just do it during the normal class hours. So the study week, I guess, is the week of March 11th. Right, so the benefit is then it's not all the lectures crowded. 3 lectures in a week is quite a lot, both for me and for you. So maybe we can have a poll on Piazza and see how many prefer doing it during the study week versus doing it on Wednesdays. Okay, so if not, let's kind of. This lecture will go from generalization issues to robustness issues, right? So both are related. I think there was a question on Tuesday on, can we think about not just generalization on a given test set from the same distribution, but something more challenging, right? So that's what we'll do today. But before that, let's recap from last lecture. So what was kind of the conclusions from the last lecture. So up till the last lecture, what we had studied was classical theory for generalization, right? So there is bias, there is variance, and the classical theory says we should trade off the two. And that's why, there was the issue of not training high capacity models, right? You don't want too many parameters in your model, because if you do, then you would tend to overfit and then you don't generalize well on new data sets. On the other hand, if you have undercapacity, if you have too simple a model, then it underfits to the data, so there is a high bias, and then again it's not good for generalization. So the classical theory was there's a middle ground, there's some optimal model capacity for which the bias and the variance are optimally traded off. So that was the classical theory. But then what recently people have found both in practice and there is some theory behind it now is that U-curve is no longer true, right? It is true up to the regime of over-parameterization. So as long as your model parameters are roughly smaller than the number of samples you have, then you are in that classical regime, right? So there, the training loss won't go to zero, so you kind of have this trade-off. But then the over-parameterized regime is where the training loss goes to zero, and the question is here, what happens to the test error when the training error goes to zero? And it turns out in the networks we train in practice, what we observe is the test error keeps going down as you increase the capacity of the model. As you have bigger models, you actually get better test error, right? And the reason behind this was we are not looking at the worst case of all models in that size of parameters, right, or in that level of model complexity. Instead, we are training these networks in a specific way using stochastic gradient descent or related algorithms, and then there's a form of algorithmic regularization that's happening there. So the way we train the network, we are not arbitrarily picking a model out of all possible models that achieve zero error, right, zero training error. So it has additional special properties, and this relates to the implicit regularization that stochastic gradient descent endows on the model. And so that's the reason that you kind of get these, the bigger the better kind of paradigm where you have a bigger model, it has more capacity, but on the other hand, there's also the potential to achieve a minimum norm, a better norm in terms of the weights of the network, and hence, it's more regularized than the network with less capacity, and hence it generalizes better. Right, so it has better error variant. Where is all the markers are on the other side. It has better bias variance trade-off because, first of all, for the bias, right? So if these are the training data, if you remember the curve I drew on Tuesday, it interpolates between all of them, right? So there is, it's perfectly fitting the training data. But then what prevents it from overfitting is, when it interpolates between them, it tries to minimize the norm, right? So it's smooth except like maybe when it's trying to fit this training sample, right? So it has like this constraint of fitting the training samples, but as it tries to do that interpolation, it is forced to be smooth in the adjoining region. Right, so that's the reason that it can optimally trade off both bias and variance, at least like at an intuitive level. So is that intuition clear? Right, because the classical theory of not completely fitting to the training data was if I do that, then I may have too much variance, in the worst case, this highly complex model may not generalize well, right? But if you can sufficiently regularize that model, then we won't go into that worst case VC bound complexity, right? And that's the idea that, these algorithms are regularizing, and it's an open problem. How do we better regularize these systems? We don't have an answer. Right, should we do L2? There is path normalization. There's a whole zoo of regularizations, right? And I guess that's the next open problem that, let's make our model very big, but then maybe can we have these additional regularizations that may further encourage these algorithms to go to a good solution, right? At the same time, still achieving zero training loss. You don't want to over-regularize so that the training loss doesn't go to zero, right? So you want to achieve that nice middle ground, and it's not clear what good regularizations are beyond just the standard stochastic gradient descent or L2 regularization. Right, so that's still an open problem. And then the other open problem was in terms of the size, right? So before we get there, one more thing what we studied was, so far this only talked about the bias variance trade-off, assuming you go to empirical risk minimizer, right? So meaning you can get to the globally optimal point on the training data, which in this over-parameterized regime is zero training error, right? So you assume that you're able to achieve that, and in practice we are mostly able to do this. I mean, there is still the issue of hyperparameter tuning and the compute cost that goes into finding the right hyperparameters like learning rates, but mostly we are able to achieve this. And there's also some recent theory postulating why you may be able to achieve this, right? What are the conditions that can lead to this ability to achieve the globally optimal solution? So again, this is very new theory, and there's still, I think, many open issues. I think the main one is this particular theory does not assume any stochasticity, right? So it's pure gradient descent and not stochastic gradient descent, but that's not what we do in practice, and noise could change some of these results. It's not clear. And the other one was, it requires a very high degree of over-parameterization, this current result. So you want these networks to be very, very wide for this result to hold. In fact, for fully connected networks, it should be exponentially large, right? The width of each layer should be exponentially large in the number of layers or the depth, which is very bad. But for ConNet and ResNet, it's polynomial, but still it's very big. So most of the time, we don't have very wide layers, right? So we overall have a large number of parameters, but not necessarily forcing every layer to be wide. So it's still not clear if this can be improved. Yeah, so that's kind of where the optimization result is. And so overall, kind of the summary was, right, it's what currently seems to work in practice is big models, right? So if you have big models, you can fit to the training error, so you can at the same time have good regularization through algorithmic regularization or other means. So you can have good generalization. It's also easier to optimize bigger models, and so you can easily get to zero training error, which wouldn't be possible for smaller models. Right, so that seems to be where the field is right now, that bigger is better, but it's really not clear if we kind of go further into that question, right? I mean, on the other hand, if there is distributional shifts and robustness issues, what happens? That's something we'll look at the robustness issues today. And kind of one passing thought here is, it's really diminishing returns, right? Because it becomes exponentially bigger model for the error to go down even by a bit, right? So if you see here, the error is hardly like 0.1%, right? To kind of go down from here to here, you need like almost like 10 to the 7 more parameters, right? So you have like this model requiring to be substantially bigger for even a smaller reduction in test error, especially when you have models where the test error is already reasonably small, right? I think that's pretty intuitive, right? So to go from 50% to 60% error is so much easier than going from like 80% to 90%, accuracy. Right, so to improve the accuracy from 50% to 60% is far easier than from 80% to 90%, right? And that's kind of where the challenge is, because as you try to go to these, as you keep asking for better and better accuracy, the requirement on your model, right, the size of your model seems to grow exponentially. So note that this is a logarithmic scale here, right? So we're going from 6 to 60 to 600. So and the payoff is like going from about 75% to 85%, right? So this requires huge models and lots of compute infrastructure, and it's not clear how to overcome that. It seems like there's some really fundamental barriers to train small models with even reasonable accuracy, right? So somehow you need these big ones, and especially if you want to get to the state of the art, there doesn't seem to be any other way, right? So it's an open problem. Okay, so that's where we stopped on Tuesday. Any questions before we move to the robustness issues? Yeah.
Yeah, I have a sense that curve that you showed,
yeah,
like that,
the double.
that's dependent on the underlying model, the complexity of the underlying model.
Mm-hmm.
They got that curve for the image.
That's actually a conceptual curve. I mean, there were also some experimental results, but they're still fairly small scale, the results that were obtained. It was on fully connected networks, I think 1 or 2 layers. Sorry, I meant 2 layers, or the first layer was random basis functions in many of those experiments. So it's really, I mean, people haven't replicated this curve at any big scale, right? They haven't carefully increased the model complexity and replicated it. So it is at a small scale and on fairly simple domains people have done, or at least that paper did, right, this paper. But yes, it does depend on the complexity of the model and our ability to optimize this model, right? Because it's assuming you're going to get to 0 training error here. There's no reason, right? Maybe for some models it's impossible to do that even if it's a big model. Was that your question?
Yeah, sort of. It just seems that if you start with different data sets, you might end up with some where you don't have that tail. Just if you have a classic curve and other data sets. But by data sets, I mean underlying models, where the data, your model from which you're getting the real data.
Right. So I guess in their paper they were looking at this noiseless realizable setting, right? So what they proved is highly artificial, but the hope is it'll extend to a bigger class. Okay. Any other questions? Yeah, so now let's look at robustness issues and ask, so far we've only looked at generalization. So we are assuming the training samples are drawn IID from some distribution, and the test is also going to be IID from the same distribution, right? I mean, this is of course an ideal scenario. I mean, in practice, it almost never happens, right? And especially the way machine learning is deployed today in real world, it's very far from true. And so one step further is to ask, can I think about the failure cases for a trained system, and then maybe can I train the system to avoid these worst case bad examples, right, or adversarial examples. And that's kind of been a very new line of research at least in the context of deep learning. So we'll also look at some historical context as we go. So why is that important? When I showed you some of those plots, I mean, like ImageNet, what are we at, 85% or 86% accuracy? CFAR, we are at 97%. So we have these very high accuracies in some of the benchmark data sets. And so that may lead some people to think, oh, computer vision is solved, right? I mean, it's far from true, and it's far from the way humans process images. And there are some very kind of striking examples of how wrong or the system can go and how easy it is to fool the trained system, right? So in this paper, they were looking at just the stop sign, they just added some boxes, right? And it got completely confused on what it was. And this is fairly benign. I mean, if you're having a self-driving car, you don't want that to confuse what a stop sign is, right? Or a face recognition system, if people overlaid some kind of sunglasses or spectacles, then it got confused. And also, this turtle here, it thinks like it is a rifle and so on. So there's all these like kind of, first of all, the errors are quite not intuitive. They're not like the errors that humans make, right? So there's kind of no explanation of why this error happens this way. And then the other is it's very brittle because, it can be easily fooled with very simple changes to the image that humans can easily overcome, right? So it doesn't fool the humans in any way, but it fools the machine very easily. And so today we'll see what are some form of attacks, like, how can we kind of attack or find these adversarial cases, right, that will fool the machine learning system, and then what are the defenses? How do we train the system to be robust to these adversarial examples? And so we'll see both the sides, and then we can ask who is winning, right, like where is the field currently? So what's some of like the simplest form of attack, right? So this notion of data poisoning is actually quite old. It's essentially like having outliers, right? So you can have like, this very nicely behaved blue and green classes. In fact, a linear classifier can perfectly separate this data, but then you can poison this data set. So an attacker can go and like start putting like blue dots on this side, right? And now you will have the issue that, you could get confused because of this poison. Right, so here you're assuming the attacker has access to the data set. So before the model is trained, the attacker can go and add some additional bad examples. And it's called poisoning because you're just kind of adding additional things, right? You're not tweaking what's already there. And so this is more an introduction of additional samples. But again, in all these models, we want to limit the attacker's ability by some form, right? Of course, if the attacker can do anything and has infinite capacity, there is no game to be won. And so usually what people do is limit the number of data samples the attacker can introduce, right? So, and it's clear, like, if there was no additional defense or a different way to train the robust system, this would severely impact the performance, right? Because, if you see this linear classifier, even with just one outlier, right, one bad example or one poison, you could have, quite a, in principle, think of it as like there's quite a lot of blue examples here. So you could tilt that line by a lot and reduce the overall accuracy on the true samples with just a few poison samples, right? So it's intuitive that you can have this phenomenon of not being robust to these outliers or poisons, right? So just a few of them can completely give a different classifier than the one you should have trained, right? So this is the ideal classifier that perfectly separates the data, but with just a few poison examples, you can be very wrong and very far away from that ideal classifier. And so this notion is not new, right? So there is the whole field of robust statistics that dates all the way back to 50s. And so people in statistics asked, now can I train a robust classifier, or can I do like now a robust algorithm that has some defense against outliers? Right, so most of these results are like these outliers can be in somewhat arbitrary positions, right? But there's a limited number of them, and then there's a guarantee that you can be robust to them. So as an example of this, we'll deviate back to some classical statistics before we go back to deep learning, right? So as an example of how to make an algorithm robust to outliers, if you recall, we did PCA a few lectures ago, right? So the PCA was finding this low-dimensional subspace in data by looking at the top eigenvectors of the covariance matrix. And so it's clear that even a few outliers can severely affect this, right? Because you have all your data samples in this subspace. Now if you have even a few of the examples very much away from the subspace, your resulting PCA can be quite different from the true underlying subspace. And so how do we make this robust? So there is a long line of literature on robust PCA, and what they aim to do is instead to separate out the outliers, right? So simultaneously find this low rank subspace and also try to pick out what the outliers are, right? So you kind of like want to come up with this decomposition of saying, my result is not just the subspace, but both the subspace and what the outliers are. Right, so that's the formulation of robust PCA. There is a long line of literature in trying to do that, right? So, the classical methods mostly try to do some kind of trimming, and there were also like convex relaxation methods. So some of the convex relaxation methods looked at like convex relaxation of like, requiring one matrix to be low rank and the other to be sparse, right? Because you can write out the optimization problem, which is to say, decompose this given matrix such that one part is low rank, the other is sparse, right? Both are non-convex constraints, but you can look at that convex relaxation and come up with guarantees. And a few years ago, we showed that in this NIPS or NeurIPS paper from 2014, that you can actually do a very simple alternating projection, right? So what that alternating projection does is you maintain some estimates of what the low rank and the sparse components are, and you iteratively look at the residual and project onto low rank and sparse objects. So meaning at any iteration, you look at the residual of M from L, so that is M minus L. And so here, the projection is nothing but thresholding, right? With a certain threshold, you threshold the entries and put them into your sparse matrix. And similarly for the low rank part, you're now looking at the PCA or low rank projection, but only on the residual. And yeah.
So to be clear, norm does work. I need to have a bound on the support of the sparsity. Is that correct?
So this will succeed under some bound on sparsity, right? So if, of course, the whole matrix S is dense, there is no hope of distinguishing the two, right? And so that's why you're like doing like a cold start. You're saying, in the beginning, I'll assume there's no sparsity, and then I'll just do PCA, right? So the first step, I'm just doing plain PCA, which is not going to be robust. But then I'll look at the residual. I'll say what is the residual? If I like just did the low rank approximation of my matrix, there is a residual, right? And so that can I start like putting this into the sparse component, and so and also to do it gradually, like you're growing this estimate of the sparse component. So as you can see, this is some form of an iterative non-convex method, right? So I haven't given all the details, but there are ways actually to show that you can not only get to the optimal recovery under some conditions, those conditions actually match with the convex methods. So there is no need for convex relaxation, at least in this setting. Right, but why I gave this example primarily is, you can come up with formulations that have inherent robustness, right? So instead of just assuming that all your data lies in some low-dimensional subspace, here I'm relaxing that assumption and saying, some data points I cannot fit into this low-rank subspace, right? So you're allowed to kind of get a free lunch here and say, okay, these data points don't fit to the low-rank subspace, and it's okay. But then you want that to be sparse and not be too large, right? So there are other settings as well where robustness is used, robust linear classifiers, robust likelihood ratios based tests. All these is like, and Huber is one of the proponents of robust statistics from 50s and 60s. So that's where the classical field was. And so now the question is, what is again the modern equivalent of robustness, right? So, and we said, for classical statistics, we will just kind of, explicitly try to remove those outliers, right? So all these methods say, try to get this to work on the rest of the data except the outliers, but also detect the outliers. You're doing both simultaneously. The outlier detection as well as classification on rest of the samples. Or in the PCA setting, it was dimensionality reduction in the rest of the samples. Right, so that's how the classical methods worked. But what happens in the case of having now a highly nonlinear model, right, and a lot of capacity in the model? So here, the situation is actually it's harder to understand, right? Of course it's harder to understand. But why is that? Because if it is now this highly nonlinear classifier with a lot of capacity, you may try to satisfy both. Like you can still keep the same separator here, but kind of now also fit this new sample. Right, so even the Poisson samples, you can still accommodate them without necessarily compromising on the original one. At least in this figure, that's what it seems like, right? Whereas earlier, this linear classifier moved by a lot. But now, potentially, you could still retain the same performance in the original region, but poison it in the new one. Right? I guess the main difficulty here is where this poison is, right? On the other hand, if this poison came somewhere here, then of course it would, highly affect the performance, right? Because even though, there is separation here, if it goes like this, then you can, have a lot of bad, errors because of that. And that's kind of, I guess, the hard part to ask, what does poisoning mean, right? Can you pick this sample very much in the interior of this other class, or does it have to be very far away, right? And actually the whole of this robustness and security or secure machine learning, the main difficulty is what is this attack model? So that's, I think, what makes this challenging, because it's still not clear what the risks are. If it's a true attacker, what that means, or if you just want this to be robust on its own without an actual explicit attacker, what's the right robustness loss or robust loss? That's also unclear. But in practice, people have seen that it's actually very easy to manipulate with data poisoning. So here I think they just put a single poisoned input, and then they were able to switch all of them, quite a lot of them. I think here they said that this, this dog is instead of fish, right, this top one here, and then I think it changed the confidence of many of them, right? So the fish class actually started having high confidence in all these other examples too.
Sorry, is that tampering with the training data set, or is that
yes.
or is that an adversarial implement test data?
No, on training. So this is all during training, right? Because the figures I showed, we are changing that classifier. That's because we're training on them, right? So this is all the training data set. And that was kind of this figure saying, right, if you now added this new blue sample, which is poison, the result from the training changes. So this is all at training time. Right, and so you're poisoning your training data and seeing what the resulting classifier ends up being. Yeah? Any questions here? Right, so So yeah, so it's not, so this is an issue because even it looks like having very small number of poisons could drastically change your classifier. And people have also shown like attacks that you can't really detect, like have some like, like part of the region be like tweak it a bit, and that also seems to completely change the result on many other examples. And it's still an open problem on how to detect these data poisons and how to completely avoid them, right? So, and so that's where, people kind of will look at some of like the min-max formulations and robustness, and most of them will look at like some perturbation of the original data and assume that under those perturbations will be robust. So these examples are showing that this is a big problem. And so, some tenets, I don't think these are practical. These are from Alex Madry and Zico Coulter's slides. I think they give some useful guidelines, but it's not clear you can always follow them in a real-world practical setting, right? So, I mean, says that, you take your data yourself, don't trust it from others, right? And same with the model, like we'll see in the model as well, we can have these attacks because you don't know how that model was trained. If the model was trained with all these like kind of what they call backdoor attacks, because you have these samples with like undetectable signatures that cause the model to do badly on certain examples. We don't know how to deal with that either. And then, of course, even we don't know what predictions it would give, right? It may be wrong on many predictions. So I don't think this is really feasible in many cases, but it's just some good guidelines that if you can try to have control on your data, on your models, and also really have a human in the loop and check the predictions, right? And in many cases it's not possible.
Does the attacks work well against GANs then? Does these same attacks work against GANs well?
What works in GANs?
Working to the GANs.
So right, what about them? What do you mean works?
Would the poisoning attacks, like the simple poisoning attacks, work well against GANs?
Oh, poisoning attacks. So again, what does a poison mean? Right, so here it's like the poison is fooling the classifier into thinking something else, whereas the GAN just generates images, right? And then you want to ask, do you want a conditional GAN like that generates for different classes? And I think people there, I'm not sure if they explicitly check these poisoning attacks, but you can imagine even there it could have an impact, right? Because like if it's all like dogs and even like maybe a few cats may end up like mixing those, like kind of a weird mix of dog and cat. So it can happen, but I'm not aware of a work that's looking at that. Yeah.
For that image that was engineered on the, like that was poisoning the training data, was that like engineered based on the initial classifier? That was created, because like if the same image was in any data set, would that also make that data set, make the model classify?
Right. So that's like this difference between like black box and white box, right? So in white box, you know what the classifier is. You're engineering an attack specific to that. In black box, you don't know the classifier. And so the both settings, the white box is certainly easier to attack because you have the model. And I'm not completely certain on these specific references, but I think these were white box. We can check them. Yeah.
The area of interpretive machine learning, where they say that neural networks, there's kind of like this. These layers are learning these features of the data. But it seems like with these kind of things, if you can just add these, even this white noise distribution, you're not really learning any features of these images. There's no, like the learning, it's not trying to extract these features. Has there been any kind of field of work that tries to take maybe a more principled approach to looking at an image and breaking it down into features and learning on the features rather than just straight learning on the bitmap of the image?
Right, so, I mean, in a way, like classical computer vision did that, right? So, and that's what we'll see later here as well. It's this trade-off of accuracy on benign samples versus the robustness, right, or interpretability. There's no free lunch. So it seems hard to get both. I mean, you can formulate different kinds of more like interpretable features, but many of them have pretty bad accuracy on just like standard evaluation on standard test sets. And so that's the challenge. So we'll see that trade-off in a bit more detail, but that's a good point. Yeah, so, how do we formulate this problem, right? So, like from the previous example, the one attack that a lot of the field has focused on is just simple, like, like a pixel-wise attack, right? So you attack every pixel, and typically you have like some kind of a norm bound on element-wise. Like at each pixel, you can't introduce more than a certain level of noise, right? So typically it's like element-wise, but then you could also have other norms. And so the idea is some kind of bounded perturbation of the input can I introduce and make that sample adversarial, right? Like, given this sample, what is the worst case perturbation, right? How do I perturb it in the worst possible way so that my loss is maximized, right? So this is an attack, so it's an adversary asking, how do I really mess up this classifier, right? How do I make this loss as big as possible on a given example? Is this clear? And so there is now, once we write down this kind of an optimization problem, we can also have the minimization as the outer loop, right? It says now, like let an adversary attack this model by perturbing the input in some space, and now I want to look at, this kind of a summation over all the samples. So I'm looking at what is the worst case perturbation on each sample and averaging them and find a model that minimizes this, right? So this model is now like trained for the worst case, right? It's trained to overcome this adversary who can go and perturb each sample, right? So I think the loss function is a natural one to think about if you are going for the worst case. Is this clear? So the inner maximization is the attacker because he's figuring out what is the worst case perturbation I can do on each sample under some norm constraints. And then the outside minimization is the defense, because now I want to minimize this worst case loss and find a classifier that's robust. Yeah.
So is this noise added to every one of the samples or just one sample?
Every one of them, right? So that's where you see this maximization is happening now for each sample, and then you're looking at the summation over all the x and y. So this is sample dependent.
So you're presenting it as somebody attacking the data, but can you also use this to determine what level of noise is tolerated in your data set to be able to do that?
Right, and I'll show you some plots. It turns out not a whole lot if you still want good accuracy. And that kind of goes back to the earlier idea that these are very brittle. So if you want high accuracy, even like here in this example, it was like 0.005, right? So very small amount of noise.
But the original picture, I'm sure, had noise in it too.
Yeah, but this is an adversarial noise, right? That's the idea that, it's not benign. It's like really trying to fool the classifier. And if it's really an adversary, just a small amount of noise is enough.
So I noticed this formulation we have here is a competitive optimization, right? So
Yeah.
It's almost like
Yes. Yeah, so if you recall like the third lecture or second lecture, we had these competitive optimization frameworks to try to optimize this, right? So and that's where it'll be useful. It'll be useful for GANs, it'll be useful in these frameworks.
Would it basically fail if you just smooth the image before smoothen the input image before you train on it?
Smoothen while fail?
Gaussian blur across the training image. The adding white noise related.
No, but in the Gaussian blur, it's just the sample independent, right? Whereas this one here, this noise is dependent on the sample. I mean, it's looking at the worst case, like what is the worst possible perturbation. So it's not white noise. It's noise that's dependent on the sample, right?
You think if you pre-process the image and then do the adversarial noise?
Sorry,
No, pre-process it, add the adversarial noise, but then pre-process the image after it.
Oh, after you
To protect against the adversarial noise.
So how would you pre-process? In a way, that's what this, I mean, then it's like, I mean, that's part of this minimization in some sense, right? It is still a defense. I mean, here I've just written this theta, and that theta could be anything, right? It could be maybe like the layers below or the layers above, it's not clear, right? I mean, this formulation allows for it, right? Because this is just theta, right? Some kind of model parameters. So you could have a modular version of first cleanup, then use the original classifier. That's one instance, right? It's not clear that's the best instance. In fact, many times it won't be the best instance because it's better to have end-to-end and look at the best possible model under these adversarial samples. Right? I mean, that what you mentioned is one instance within this minimization, it may not be the best. Right? So, I mean, in this two-player game, there's the attacker, the adversary, and then the defense, which is the robust classifier. So just a short summary of like the research so far. I mean, these are according to Zico Coulter, whose slides I'm showing here, right? I mean, it's still very much like an evolving field. So there is, every day you'll see another paper on attack, then there's a defense, that defense gets broken. So, and that's because it's quite hard to come up with provable frameworks, right? So when there are no guarantees, I mean, it's these things can be pretty much gamed, ironically. So there are all kinds of like claims that people make, but then there are also counterclaims. So I think what I want to mainly say is, if these are mainly going by heuristic, there is still no kind of consensus on what's achievable and what's not, right? So for instance, like distillation, prevents attacks, there's a paper saying that, and then there's another counter paper saying many examples where it doesn't prevent attacks, right? And then there are like these perturbations more in translation and rotation, and there was the intuition that it's robust to that because convolutional networks are actually translation invariant, right? But then there are specific attacks where you can still kind of full networks, especially with rotation, right? Rotation can be quite bad on these networks. And there's a whole ton of defenses, but then, many of them are also broken even before the review period. So there's a lot of like this back and forth, but it does seem like, it's quite easy to attack these networks, and the defense is very, very hard, right? So that's kind of the consensus that, like generating this kind of like adding small amount of noise and fooling the classifiers, it's quite easy to do. But to train a very good robust classifier that overcomes these attacks is very hard. And especially, there's no free lunch. The accuracy can degrade by quite a lot when you're trying to have a defense against these adversarial examples.
But these sort of coming with these adversarial examples sort of assumes the knowledge of whoever is the attacker, knowing exactly knowing the exact structure of the network. Under some uncertainty about how exactly the network is working, how easily does that sort of prevent the attacker from attacking?
So I'll address that. So that's the white box versus black box, right? So we'll see some of the white box methods, and then what the black box methods do is mainly like assume some limited query, like you can still query in a limited way, and then they try to estimate the quantities that these white box attacks will need, right? So it's still possible to do black box attacks. It is harder, but it's still possible to attack.
So in terms of these, I guess, of many security applications, it might seem like a possible thing to say, there's like sort of more general sort of, like let's say I have some self-learning cars, I have a more general structure of these models that I deliver to every one of them, and then I try each individual model to change some side things to make it difficult for attacker to systematically find the attack, right?
So I'll come to let me go through the Whitebox attacks, and then you can see the intuition of how you could do a black box, right? Yes, it is much harder to do black box, but there are still some ways to get around that. Yeah. So let me come to that. Yeah. Anything else? Yeah, so let's first look at the adversarial side, right? How do I do this inner maximization? I think this is fairly straightforward, right? What you have is an optimization problem. This is going to be non-convex, because all these networks are non-convex, but it's fairly intuitive to think that you could do many things. Right, so you could just do a local search method, right? You only take some gradient step rather than doing the full optimization, or you could actually solve the combinatorial optimization, which is hard, or you can do a convex upper bound, right? A convex relaxation. So this is fairly standard. This is how you would go about approaching any non-convex optimization. But let's kind of quickly go through them to kind of just make sure it's clarified. Right? So if you're trying to do local search, you would do gradient descent, but there's a projection needed, right? Because this delta now has some norm-bound constraints, so that's this capital delta. So all you would do is project it back into that constraint, right? So this is the standard projected gradient descent. And as I said, the most common norm is this L infinity norm, right? Meaning at each pixel point, you have some bound on how big the noise can be, right? What is the upper, it's between some, let's say, minus epsilon and epsilon, right? So that's the bound. And so if you have to do the projection, it's nothing but clipping, right? So if you have this epsilon, it's nothing but the projection function is just a simple box constraint, right? So this is straightforward. And another kind of thing is, now what's the step size? If you're doing local search, you also have the step size issue, right? The alpha is the step size. How big of a step do you take in the gradient direction? And if you send that step size to infinity, this is nothing but the sine function, right? So this is where you have now this kind of, the optimal noise is according to the sine of the gradient, right? And so it's called the reverse gradient because, in your, when you're training the model, you're doing a gradient descent over the loss. Right, but now this is gradient ascent, you're reversing the gradient, and in a way that is the adversarial thing to do locally, right? Because the worst you can do is go in the opposite direction of the gradient. And because of the norm constraint here, it ends up being just the sine of the gradients. Is this clear? Right, so this is coming from projecting the gradient onto the L infinity ball and then letting the step size go to infinity. Yeah? Right, so this is fairly intuitive. So, what the adversarial sample is doing is it's trying to go in the reverse direction or the reverse gradient direction, and that's how you can get your adversarial sample. And if you want the defense, right, if you want the outer minimization with respect to this particular maximization, you can always do this, right? So you can get now this reverse gradient here, right, the noise according to the reverse gradient, and then you keep optimizing your loss function on mini batches, right? So this is fairly straightforward. So you do the inner maximization, you take this local update as this reverse gradient, and now you do the outer minimization also as a local update on a mini batch, right, a local search update. Any questions here? Yeah. No? So yeah, and this does give some level of robustness, right? So I guess this is the test error on adversarial samples. So if you have now your test data set to be adversarially perturbed, the standard COMNet can have, so I guess this is the PGD. Yeah, so in the robust one, you have like very small test errors, whereas, oh yeah, so this is without the defense, right? So you still have the adversary. So the clean is like, there is, of course, the standard train and the standard test. So there is no adversary there. Whereas the fast gradient update means there is the adversary, right? So that's the attack. And then this projected gradient, I think, is some other projection, like, similar. And so here you can see, like, without the defense, you can get very high adversarial test error, but now with the defense, you can reduce that. But again, this is not provable, right? So this just kind of is a heuristic saying you could hopefully achieve more robustness, but there's no proof that it does.
So in that, like, delta star would depend on theta.
Yes.
So when you take the gradient, do you treat delta stars? So like.
This is delta star. This is.
Yeah. So on the next slide, when you then take the gradient respective theta, are you backpropping through the backprop that you use to compute the delta star, or do you treat that as a second given fix?
So you would because you want to like backprop through all of this, right, on the theta. That's what this expression says, right? So you are, yes, plugging in delta star, and then you're backpropping through this whole thing. So you're perturbing your sample, and then backpropping through that. Is that clear?
I say, are you backpropping because like there's a theta that comes from the loss of just like the adversarial example under theta, and then there's how could you change theta so that the adversarial example itself is different?
Right, so you would backprop through all of that, right? That's what this expression would mean. So indeed, this delta star is also a function of theta, but so you would incorporate that. Right? Without it, how can you not incorporate it, I guess, right? So, sorry,
if not, like, you would still be backpropping on the theta in the loss calculation, in this loss calculation.
That's right. So you would wherever in this loss calculation, wherever there is theta, you would like backprop through, you would take the derivative with respect to all of that. Is that answer? Yeah. Any other questions? Right. So this is fairly intuitive, right? So if you have a min-max problem that's non-convex, you can take a local maximization, then a local minimization, and you hope for the best, right? There's no guarantee that this does well. In fact, if you recall the lecture on competitive optimization, the simultaneous gradient updates can actually oscillate, right? And they can oscillate in the simple case of bilinear games. So this is actually not necessarily the right thing to do. It's not according to theory, but it's simple, so people do this. So there's indeed the opportunity to look at better methods to do robust learning through better optimization techniques. And so one set of things that you could do is go into the inner maximization, and instead of like just doing a gradient update, you could like, look at the combinatorial optimization and then come up with convex outer bounds, right? So this is provable, but then this is actually at the same time more expensive, right? So if you recall here, this non-convexity is coming from ReLU. If it's fully connected, right? So you have this ReLU. That's the only kind of like source where you get this nonlinear update. And so you could ask that, yes, in general, the output of a network of ReLUs will, be non-convex, right? The set, even though you start with these nice convex sets, it will become non-convex at the output. But then you can come up with a convex outer bound and then make the constraint that this is still like, right, not violating the boundary, right? This entire set is on this side of the classifier boundary, right? So that's the notion of having a convex outer bound, right? So then with that outer bound, you're guaranteed that this whole set here is also robust, right? So you cannot, an adversary, even though perturbs anywhere, they're in the input, right? So any perturbation here in the input will be robust, like it won't be confused by the classifier. So this is provable, but the challenge is these bounds could be loose, right? So we don't know how big this set gets. And so you're trying to defend this whole big set, which may then reduce accuracy and come up with all other, not so desirable characteristics. But that's on the, so that's the thing. If you want provability, there is something else you have to pay, but this is impossible to do. Any questions here? Right, and so there are several ways to go about doing this convex outer bound. You can do the convex relaxation and just solve this in the primal, or you can go to the dual space and do it there as well. Right, so I won't go into the details, but just kind of so that you're aware, you can also just look at a feasible solution in the dual and kind of use that as an update, and that's cheaper than doing it in the primal. And then there are ways to kind of do iterative lower and upper bounds. If you see here, it's really this kind of lower and upper bounds that come up, right, in the relaxation, and then there are ways to make this also iterative and more computationally feasible. So, I didn't give the details, but the main idea with all this is to come up with like now a modified loss function, right? That's essentially what's happening, right? This inner maximization is now changing your loss function. And in a way, the same as in GANs, right? If you don't know what is the right loss function to optimize for, you solve another optimization program to come up with what is that appropriate loss function. And so in a way, in the robust setting, it's like a worst case, right? Like what's the worst you can perturb a sample that modifies your loss function, and you're still doing this backprop on this modified loss function. And the nice thing with this convex outer bounds framework is, it all becomes like differentiable. So you can kind of do this entire like minimization and maximization through auto differentiation. So there are some nice properties you can obtain while still having the provability. So I didn't go into the mathematical details, but I hope you kind of see the main picture is like this convex relaxation, right? Like you're looking at a convex outer bound of your original sets, which are non-convex, and then you're ensuring that these convex sets are robust. So that means the classifier is able to separate them. So that's the main idea behind now having a provable one, because you can now prove that your entire set is robust, right? Because the convex program, we can get the exact maximization. Is that clear? Yeah. So now we'll turn to like robustness versus generalization. Right, so I think, so in the last lecture when we were talking about generalization, we said just, assuming that the test data is the same IAD sample source train is very artificial, so in the real world it may just not happen. And this other extreme was robustness, right? There is an adversary who really tries to look for the worst case, right? Is really trying to get the classifier to fail, and how do we avoid those failures? So that's the two extremes. And the question is, how are the two related? If you now try to make a network robust, what happens to generalization? So what's your intuition? So this is the standard network, right? So in a standard network, you have your train and test, and you hope that they're quite close. Typically you would never get the test to be the same as train, right? It'll be slightly smaller, but if the network generalizes well, hopefully this gap is small, right? So that's what standard training would give you. But instead, if you have now a defense against these adversaries, so you have a robust classifier, what do you think will happen to generalization?
I have a question.
It's just iterations.
Oh, okay.
So it's kind of saying ultimately like you will have your training go to like 100% accuracy, and the test will not be 100%, but hopefully not too far away from it. There's some gap, but you still have fairly good generalization. That's all this plot is saying.
But they're being evaluated in different sets. Like,
One is train, the other is test. So the evaluation is test. Any other questions? So what do you think would be a plot for the robust classifier?
You would expect to see the training accuracy drop, but the gap to be small.
The gap, so again, let's define two things, right? So there are two settings. One is the test set is the standard test set, so that's just IID samples, or the test set is also adversarially perturbed. So let's look at generalization in two different scenarios. So which one are you talking about?
I was just thinking in the case of just the standard training and test data.
Okay, so by test data is the same as the original, it's just IID, but on training, we're looking at the adversarial perturbation and coming up with a robust classifier. So in this scenario, what was your thinking?
Like if you have adversarial examples in the test data, then I would...
No, on the train.
On training.
No, that's what you thought, I thought you were saying, or no?
I would expect the gap to be smaller for the robust case than for the standard, for the network trained without the robust.
Can you kind of repeat the whole thing? Which setting is this?
So I expect the generalization gap of the robust classifier to be smaller on the adversarial data than the same gap would be for the standard.
Okay.
Trained on the same data.
So what people have found consistently is actually the opposite. So it's quite a big gap on how it generalizes on adversarial. So both the train is adversarial, the test is also adversarial, right? So both are perturbed in the adversarial sense. And so this is a big challenge, right? So I mean, we hope that the robustness actually helps generalize better, right? But there are several reasons that's not true. But also I think there is maybe an optimization and a generalization issue too, right? So on the train, yes, it is like still going to 100% accuracy. So we're able to train with even this adversarial setting, which is interesting. So that means maybe the optimization is not an issue, but something else is happening. At least in this case, but several papers have kind of consistently seen a similar phenomenon that the generalization is really poor. So especially if you adversarially perturb your test samples.
But we do not test on the normal test set, right? Because in real life we do not have this.
Yes. So there was also that plot. Where was that? So yeah. It turns out that it didn't improve much from before, right? So there is the gap. I mean, here the train also kind of became, yeah, so I think the overall kind of statement there is it doesn't seem to help that much with respect to the standard generalization. So even if you adversarially perturb and do all this robust training, it doesn't help you in terms of standard generalization much, which is what you were hoping for.
Maybe we can understand because you do adversarial training, you add something to the noise, which means you train the image which doesn't come from the actual distribution.
Yeah.
Which means you train on the data set that could be either have some offset or not overlapping with the original distribution. So you may think that it's more robust, but the robustness only compensates for what we call artificial noise, but not for the
actual inherent, exactly. So we have to now deal with this distributional shift. right? So robustness is a different measure from generalization, right? Because generalization is averaged over the distribution, whereas robustness is asking for the worst case. And you can see that here, right? So, and you can see actually it made it worse, right? So it's like not even that it's kind of like somewhat the same, it also hurt the original generalization by doing robustness.
Is this happening because maybe the robust optimization is just throwing out data points, like outlier data points, and steering it toward like bad generalizations?
Right, so it is changing the distribution, right? So, and whereas now if you're evaluating on test set that's the original distribution, there is a distributional shift. So that I think is part of the reason why it's not working, why it's actually hurting generalization in the standard sense.
So why didn't they reform data and just generate adversarial points, but then retrain so that it helps steer it back towards the user optimization?
So how would you go about doing that? What would be the objective? That
I think basically, like, say, like you have a training set, you get an output, but then add noise to some of the training sets, and then see how they shift the distribution, but then you retrain it to correct back.
Yeah, so it's not clear then how much of that perturbation is enough. I mean, any perturbation of your training data is going to change the distribution. And so it's not clear how you would change it so that the distributional shift is minimal, right? So that's a tricky one. I mean, what really I guess we don't know how to do is we want to like look at interesting perturbations, right? Not necessarily the worst case. I mean, like, you know, what humans don't perceive, like, you know, you add this noise for humans, it's still, you know, the same chair, right? It doesn't change. So you want to like look at all possible distributions that, you know, the human can tell or, you know, or is kind of not affected by, but we don't know what that space is, right? I mean, that space certainly changes the distribution, but then how do I again evaluate this, right? Like, so there is a lot of mystery on both how to introduce the relevant perturbations, like what are interesting attacks, both from a security viewpoint or just the viewpoint of being robust, and then how to evaluate this on what should be the test set. That's also not clear. Right, so it's not clear. I mean, this is a specification issue. We don't know how to specify what's the right thing to do.
Is the problem also maybe related to the fact that when you're recognizing objects, you're just not necessarily able to pick up with feature invariant, but just like invariant size and invariant features? Is that part of the problem here? Right,
because you don't know again what are these perturbations that, you know, human vision cannot perceive, but you can introduce to the system. What is that space?
Maybe there's some aspect of human vision just that's genetically hard coded that we learn, but it's hard coded already.
Yes.
We need to implement that.
I agree. We don't know what that space is, right? That's the hard part. Yeah. Right. So I mean, if you're going for robustness, it seems like too much to ask in many ways, right? Because, you know, it's hurting standard generalization, so you're asking for this worst case, you're going to hurt the average case, right? Roughly, that's kind of what's going on. And then, of course, if you want to generalize for the worst case, it's still very hard to do. And that's, I think, because on the test data, if you're doing at this adversarial perturbation, that space is still very big. So it's very hard to generalize on that space. So it's still a very open problem how to generalize in an adversarial way, right? So we just don't know. I mean, even on, I think, reasonably small data sets like MNIST and SHV, and like forget ImageNet, right? Like even on small data sets, generalization becomes an issue. I mean, no one has even done like an ImageNet scale robust classifier yet, right? Provable or not. So that's the issue, right? This is, the generalization appears to be a really hard one with robustness. And one hypothesis of...
Actually, you said no one has ever done robust ImageNet?
That's provable, like, you know, in the sense of this min-max.
This is because of the scalability.
So there is a scalability issue, but I don't think that's the primary issue. So so one of the hypotheses is that I think you need way too much data than what's currently available, right? So this is one of the results from last NeurIPS, I think from Alex Madry, that says that it requires significantly more samples to generalize in an adversarial setting, right? And that's kind of the earlier intuition I was talking about, right? On your test data, if you're adversarially perturbing, there are way too many possibilities. So during train time, you need a lot more data to learn all these possible perturbations. And so, for instance, you could have like a setting, like as an example, where you could just have like one sample for the benign setting, but require a lot more samples to get an adversarial classifier, right? So it's intuitive that you need far more samples, and that may be an issue. Because for instance, like at ImageNet, you have barely a few thousand samples on each class, right? And that's just not enough to look at all these variations over adversarial perturbations. So one may be like data being the bottleneck, and some of the others, right, are that this is an inherent trade-off, right? The other bottleneck is you can't have both generalization and robustness at the same time. There's no free lunch. And the intuition is, I think, the worst versus the average case, right? You can just have one objective. Either you optimize for average accuracy or you optimize for the worst case, right? You can't have one that's equally good at both. And the intuition comes kind of because in robustness you are discarding certain correlations, right? So you're saying now if I perturb, some correlations are not going to be good correlations, so I'm going to ignore those because perturbation will destroy those correlations. But on the other hand, if I only want generalization, I'm going to exploit all those correlations, right? And so that's why there is going to be a trade-off, and I guess